Hello everyone and welcome to the third video of the SDL 2.0 tutorials. In this video we're going to create a base class for all our game entities, and the framework that we're setting up is so that you can create any kind of game that you want to make in SDL, but most likely the game we're going to end up making is Galaga. But with this framework you should be able to make any kind of game that you want. So let's go ahead first and create a few helper functions that we're going to need and structs. So first off, let's make a header file and let's call this one math helper. And if not defined, math helper underscore h, define math helper underscore h, and if. So this header file will contain a few structs, and for now a single struct and a few functions that are going to help us with the math that we're going to be using. So the first thing that we're going to do is include math.h, and define a couple of defines. So define pi, and this will be 3.14159.265, and we'll also define degree to radian. And as you might have guessed, it will be a variable to help us convert from degrees to radians. So this will be pi divided by 180.0. Now that we have that, we can create our struct that we're going to be using, and this will be a vector2 struct. So struct vector2, and this will take a float x and a float y. And then let's create the constructor for it. So vector2 float underscore x is gonna have a default value of 0, and float underscore y, which is going to have a default value of 0 as well. And we might as well initialize our values. So x is gonna be equal to underscore x, and y is going to be equal to underscore y. And this should be it for our constructor for vector. Next up, we're going to create a few helper functions in our vector. So float magnitude squared, which will return the magnitude of our vector, squared. So this will just return x times x plus y times y. And next we'll do a float magnitude. This one will be returning the square root of x times x plus y times y. So we're doing it this way because sometimes we just want the square of the magnitude without having to do the square root. So we can test things much faster using this, but if we want the actual size of the vector, we are going to be using magnitude. And finally, we'll do a vector2 normalized. And this one will return our vector2 that we created, but a normalized vector, so just a directional vector of that vector. So we'll do a float mag, which will be our magnitude. And we're just going to return a vector2, which will be x divided by the magnitude as well as y divided by the magnitude. Okay, and this should be it for our vector struct. So just a few helper functions and our struct. Next up, we're going to do a few operator overloadings so we can add two vectors together, subtract them, and so on. So inline vector 2 operator plus const vector 2 . Okay, so const vector 2 left hand side and const vector 2 reference right hand side. And this will just return a vector 2 of left hand side dot x plus right hand side dot x and left hand side dot y plus right hand side dot y. Okay, of course we'll do the same thing for minus, so that will be subtraction, subtraction, and subtraction. Okay, and there is one more function that we will need, and that is to rotate a vector. So inline, actually we don't really need a line for that. We'll do vector 2 rotate vector, and this will be vector 2 reference vec and a float angle. There we go. And this will be a bit of trig, so we'll have a float rad to angle, which will be equal to a float casting of angle times rad degree to radian. Let's just call that rad angle. So this is our angle in radians, because all the sine and cosine functions in math.h use radians, not angles or degrees, so that's what we're going to do. So we'll be dealing with degrees and just converting it to radians whenever we need to. And finally, return vector 2, which will be a float cast of vec.x times the cosine of the radian of the angle minus vec.y times the sine of the radian of the angle. So this should be good for our x, and then we just have to do our y. So for our y will be the same idea, float cast of vec.x times sine of our radian of the angle plus vec.y plus times the cosine of rad angle. There we go. So for the most part, this should be it for our math helper functions. There we go. So let's see here if we missed any angles, any brackets. We have our closing bracket here. We have our closing bracket. We probably need a closing bracket for that, and there we go. Okay, so all this would do is to take, let's say we have a vector here and we want to rotate it by a certain amount of angles. It would give us, so it would rotate this point right here over there to a point right here and return that as a vector. So this is all that this function is doing. Okay, now that we have everything set up, we can start on our base class. So for our base class, let's create a filter and call this one entities, and we'll do the same thing in the source. So entities, and we'll create a new game object called a new header file called game entity. And we'll do our define. So if not defined, game entity underscore h, define game entity underscore h, and then end f, and then our class game entity. So game entity will be our base class for every entity that we create. So if we have a texture, a sprite, or a game object, for example, a bullet or a ship or something, they would all inherit from game entity. So first we'll make a public section, which will be an enum. We'll call this one space, and this will be either local, or which local will be equal to 0 and world will be equal to 1. So this will just tell us if we're dealing in local space or world space, and that will come into effect a little bit later. We will have our private variables, which will be a vector2 and position. So since we're starting to use vector2 now, let's include our math helper.h. So we have vector2 position, we'll have a float m rotation, as well as a boolean of m active, so that will tell us if the object is active or not. And finally, a game object, a game entity pointer, and we'll call this one m parent. And the way that this is going to work is that we are going to be able to get one game entity and make it a child of another game entity. And this will give us a lot of ways to actually link objects together. For example, we can link one object and make it a child of another object, and then if we rotate the parent, the child should rotate along with the parent. So if we have 5 objects attached to one parent and rotate the parent alone, all 5 objects should rotate along with it. Next up, let's do our public functions. So we'll do game entity, so constructor. This will take a float x, which will be by default 0, and a float y, which will by default will be 0 as well. And then our destructor, and then void position, which will be the setter for our m position. So since it's the setter, it will take a vector2 of position, and then as well as our getter. So vector2 position, this one will take a space, and by default it will be world. So what this is doing is that it's going to be our getter for our position, and this will, and space will just tell us whether we want the local space for that variable or the world space. So local space will be relative to its parent, and world space will be relative to our normal grid. Next up, we'll do the getters and the setters for rotation as well. So void rotation, float rotation, and float rotation space, which would be world by default. So same idea as position, as m position. This one will return our rotation in either local space or world space. And then void active, which will just be the getters and the setters for our active. So boolean active and boolean active, that will just return our active state. Void parent, so this will be the function that we will be able to set our parent. So to either so if we set it to null, our parent will be, we won't have a parent. If we give it an object, our parent will be that object. So game entity, pointer parent, and finally game entity, pointer, and that will have parent. Parent. So that will just return our parent. And the final two functions will just be two virtual functions, update and virtual void render. These two will be overwritten in the children to do their own updates and own renders in there. Okay, so now that we have all of this done, we can get started on the CPP for the game entity. So we can go ahead here and add a new item, game entity, and in this we will include game entity.h. Alright, so the first thing that we'll do is to deal with the constructor. So game entity, our m position, we need the parameters, so that will be float x and float y. Our position.x is going to be equal to x. Our m position.y is going to be equal to y. Our rotation is going to start off as being 0, and active will start off being true. And finally, m parent is going to be equal to null. So our parent is going to start off being null. Next up is the destructor, so game entity destructor. Not a whole lot to do here. We'll just say that our parent is equal to null, just in case the parent was changed. And now we need to deal with the getters and setters. So these two. So void game entity position, and we can do a vector2 position, and all we'll do is just say m position is going to be equal to position, and then vector2 our getter now. So game entity position space space. Okay, so that's when it gets interesting. So for this, for us to get the local position for the object, it's not too hard, since if the space that we pass it is local position, we can just return our m position. So if space is local, we can just return m position. But what if the space that was passed in is world, but our parent was null? Then if our parent is null, then we can just pass back our m position as well. So or m parent is equal to null, then return the m position, and that's it. Otherwise, we need to return the parent's position, so m parent position, which will be the world position, plus, and that's when we do the rotate vector function. Because what happens is, if let's say we have the parent object right here and the child object right there. Now, if we return the world position, if the parent was rotated, let's say 90 degrees, then the child object would end up right here. So the position of the object itself changes depending on the rotation of the parent. And this is what we're going to do. We're going to rotate the position, the local position of the child, by the amount of rotation that the parent has. So what we can do is just say rotate vector, and like we said earlier, we'll pass our position. So we want to rotate our position by the amount of rotation that the parent has. And this will be the parent's local rotation. That's all we care about. And that would be it. So just to recap, if the space is local or the parent is null, we'll just return our normal position. If the parent is not null and the space is world, we want the parent's position added to the local position after it's rotated by the parent's rotation. And next up is the rotation. So void game entity rotation and float r. So this is the setter for rotation. We'll say m rotation is going to be equal to r. And then if m rotation is more than 360, m rotation minus equals 360. Otherwise, if m rotation is less than 360, m rotation plus equals 360. So that's just to keep our rotation between 0 and 360 degrees. Now moving on to the getter for the rotation. So the getter for the rotation will have the same idea as the position. We just don't have to rotate a position for that. So we'll say float game entity rotation and then space if space is local or the parent is null, parent is null, just return m rotation. Otherwise, we will return the parent's rotation, which is the world rotation for the parent, plus our current rotation. And that would be it for our rotation. For active, that's pretty straightforward since no calculations need to be done there. So we'll say first our setter, so void game entity active, boolean active, so we'll pass it in. Our m active is going to be equal to active. And next up is our getter for active. So the getter for active will be boolean game entity active, and this will just return our m active. Moving on to what's next, which will be the parent. So for the parent, for the setter for the parent, we'll do game entity parent, and it's going to take game entity pointer parent, and m parent is going to be equal to parent. But keep in mind that our local position changes once you parent an object to another object. For example, let's say the parent started off at 100 and 400. And our child started off being 100 and 500. Now, before it had a parent, the child object's local position was 100 and 500. Now, once we attached it to this object right here, its local position became relative to this object. So relative to this object, our local position would be 0 and 100. And this is what we're going to do, is just take the position of the child, the original position of the child, and subtract it from the world position of the parent. And this is what we're going to do. So m position is going to be equal to, we want to get our world position and then subtract it from the parent's world position. And the main reason why I didn't just use M position here is because this object might have been a child of a different object. So by doing it this way, we're just getting the world position for that object. So this should be it for parent, and then our getter for the parent. So game entity pointer, game entity parent, and this will just say return parent or return M parent. Okay, so almost done. Finally, we just have to do the update and the render. So void game entity update and void game entity render. And this will be it for our game entity class. So this will be the base class for everything that we do. And we can try out this class really quick to make sure that everything is working correctly. So in our game manager, we can say include game entity.h, and let's create two objects. So game entity pointer parent and game entity pointer child. So mchild. Now in the game manager, in the constructor, we can create these two objects. So the parent, let's say the parent, let's use the same idea from here. So the parent, let's set it to 100 and 400. So new game entity 100 and 400. And the child will be equal to a new game entity of 100 and 500. Now that we have that, we can just set the parent of this as mParent. So mchild parent is going to be mParent. As you can see here, mchild's local position should be 100 and 500. So if we do something like print f child local position is going to be, let's put in two floats and then a line break, and then let's test it out and make sure that we got it right. So mchild, let's get its local position .x and mchild local position .y. Of course, that would be game entity local and game entity local. So if you're trying to get the space in outside of the game entity class, you have to use game entity : and then local. Okay, so let's do that, and then let's repeat that again out here. So right before we parent and right after we parent, and let's see how it turns out. Oh, a few errors. Rotate vector is, oh, okay. So if we go back to math helper, we probably need inline here. There we go. So we might want to stop the delta time because it's just moving everything down. So we're just removing the delta time output from the loop so that we can see the position of the child object. And there we go. As you can see, it started off as being 100 and 500, just like it was here. And then after it became a child, it became 0 and 100, so relative to its parent, and that's its new position. So in the destructor, we probably should have deleted that before we ran it, but delete mParent and delete mchild. And let us now try the world position. And let's see if the world position of the child changes at all after it's parented. So there we go. So the world position of the child before it was assigned a parent, it was 100 and 500, and after it was assigned a parent, it was still 100 and 500. So everything seems to be working correctly. So the last thing we can test is the world position of the child if we start rotating the parent. So if we do that, let's go back here again, and let's start outputting the child's world position from here, but after we rotate the parent. So we'll say mParent rotation is going to be, so we need to give it a float, so it's going to be mParent rotation local plus 0.1f. So game entity local. So all we're doing is taking the rotation of the parent, adding 0.1f to it, and adding it to our rotation, setting it as our new rotation. So we're rotating the parent over time, every frame, or yeah, every frame that we run, we're rotating the parent a little bit. And let's see the output that we get from that. Actually, let's also show the parent's rotation so that we know what's going on. So parent rotation, all we need is one float for that, and this will be just the parent's local rotation. So we can take all that out. There we go. So we just want the parent's local rotation, and let's see how it goes. If we try to run it now, and there we go. As you can see, the position of the child is changing, the world position of the child is changing over time. And as it's changing, as the parent is rotating. But it seems like the parent's rotation is going up to 500, which shouldn't be the case in our setup. So if the parent is more than 360, the parent minus equals 360. If the parent is less than 360, the rotation, or if the rotation is more than 360, it's plus equals 360. Huh, interesting. For some reason, rotation is still being set higher than 360. Let's see what's going on here. So the rotation was less than 360. Oh, wow. It's been a long day. Okay, so if the rotation is less than 0.0f, that's what was going on. Okay, so if the rotation is less than 0.0f, we add 360. So since it's less than 0, we just add 360 to wrap it back around. Okay, now it makes a lot more sense. There we go. And let's pause it at 90 degrees so that we can see if what we did actually works. There we go. So at 90 degrees. So after 90 degrees of rotation, the child is at position, let's see, 90 degrees of rotation, the child is at 0 and 400 on the Y. So the child used to be at 100 on the X, and it rotated by 90 degrees. So it should be here now, and it should be 100 minus the position of the parent. So it should be at 0. And its position relative to the parent, so the parent is at 400, and it should be the same as the parent. So it should be 0 and 400. So if we check it here, it's 0 and 400. So as you can see, now we have a way to attach game entities to each other as child and parent. And if we do any transformations on the parent, it's affected, the child is affected by it. And this will be very helpful, especially if we have one object made up of multiple sprites. We can put all these sprites as a child of that object and then move that object and all the sprites would move along. So this will be it for the third part of the SDL 2.0 tutorial videos. In the next video, we are going to be finally creating our first texture, the texture class, which will inherit from GameEntity and output that texture onto the screen. It has been a pretty long video, longer than usual, but I really hope that this video helped. And if you have any feedback, comments, or suggestions, please leave them below. Thank you very much for watching, and I will see you next time.